Hello everyone, my name is Konda. I'm a PhD student from the Department of Mechanical Engineering at the University of Nevada, Reno. The title of my paper is Modeling and Inverse Compensation of the Quasi-Static Voltage Strain, Lonely Stroke and Hysteresis in Supercoiled Polymer Artificial Muscles. This paper has been co-authored by my advisor, Dr. Zhang. Artificial muscles are materials which change shape upon the application of external stimulus such as heat or voltage. Some examples of artificial muscles are presented in this slide. Fluidic actuators and SMA actuators vary in length upon the application of pressure and heat respectively, whereas DEAs vary in area upon the application of voltage. Artificial muscles possess many advantageous properties such as compliance, compactness and lightweight, and are capable of generating motion without using many rigid parts. Due to their advantageous properties, artificial muscles have been used in many areas including medical robots, robotic exoskeletons, aerospace applications, and in robotic arms and fingers. Supercoiled polymer artificial muscles, also known as SCP actuators, are artificial muscles which generate linear actuation upon the application of a temperature change. They are made from conductive nylon threads and are capable of generating 21% linear stroke and also exhibit 27 watts per grams power density. In addition, they also exhibit an operating frequency of 0.3 Hz in still air and an operating frequency of 1 Hz in forced air. Due to these desirable properties, they have been applied in various robotic applications including robotic arms and fingers and soft robotic end effectors. The behavior of SCP actuators is studied by analyzing the relationships between three key parameters: strain, temperature, and load. Due to the lack of temperature sensing capabilities in SCP actuators, voltage is used as a temperature surrogate, and strain, which is considered as the output, is modeled as a function of temperature and load. This relationship is highly nonlinear in nature due to the presence of two nonlinearities, which will be discussed in the next slides. Hysteresis is a common nonlinearity found in many smart materials and electromechanical systems. The output of a hysteretic system not only depends on the present input but also the history of inputs, and this is valid for quasi-static values as well. In SCP actuators, the relationship between all three key parameters are hysteretic in nature, leading to the presence of three-dimensional hysteresis. Another important nonlinearity which has not been studied extensively is termed as the lonely stroke or the lonely curve. This behavior is demonstrated in the voltage strain relationship of SCP actuators when the load is switched from 300 grams to 200 grams in this slide. As it can be seen, when continuous voltage cycles are applied to the SCP actuator after the load is switched, the first output cycle, which is plotted in red, is different from the second output cycle, which is plotted in blue. This first output cycle is called the lonely stroke, and this behavior has been observed in both the load strain and voltage strain relationships of SCP actuators. Besides SCP actuators, the lonely stroke behavior has been observed in other artificial muscles such as pneumatic actuators, SMA, and SMP actuators. However, no systematic study has been done in this area. Including the lonely stroke in modeling is crucial since artificial muscles are used in areas where non-repetitive tasks are to be performed. In such scenarios, lonely stroke will always appear when external conditions are changed. Also, as shown in the figures, lonely stroke presents complex coupling with the repeatable hysteresis. Therefore, if lonely stroke is not included in the analysis, it would lead to large discrepancies which would further lead to safety issues. Therefore, this is the first study to systematically model and inverse compensate the lonely stroke and hysteresis behavior. We primarily focus on SCP actuators in this study. However, the results can be generalized to other artificial muscles as well. In order to capture the lonely stroke and hysteresis behavior, we use a popular hysteresis model known as the Prisarc operator. The output of the Prisarc operator is determined by delayed relays called hysterons. Each point in the Prisarc plane is a hysteron, and the output of the hysterons is shown in the leftmost figure, where if the current input is greater than alpha, then the output is +1, and if the current input is less than beta, it is -1. However, if the current input lies between alpha and beta, then the output will be the same as the output of the previous input. The output of the Prisarc model is a weighted sum of the area of different cells in the Prisarc plane as shown in the center figure. It is represented by this equation where UC is a constant bias which enables the operator to output a non-zero value for a zero input. Sij is the area of the cell ij which is determined by the histograms present in that cell. For more details, please check out our paper. Another important aspect of the Prisarc operator is that the output at physically feasible minimum and maximum inputs is constant and not history dependent. Now let us consider that the input sequence shown in the left figure is applied to a system which is both hysteretic and also exhibits lonely stroke behavior. When we do this, the correlation shown in the right figure is obtained. As it can be seen, the output at the physically feasible minimum input I min is not a constant but history dependent. Therefore, the Prisarc operator cannot be directly applied to model this behavior. However, if the input range is extended below I min to a physically infeasible value IEXT like this, then the correlation could be transformed to look something like this. Now, this form can be easily captured using a Prisarc operator. Please note that the points plotted in red do not exist in reality but are only present in theory. Extending the input range implies that the Prisarc plane is constructed using IEXT and Imax rather than Imin and Imax. This leads to the inclusion of additional columns towards the left of the Prisarc plane, and the output of this extended Prisarc operator is represented by this equation. Due to the extension of the input range to physically infeasible regions, results in the density function being classified into three types. The sigma densities and cells act as the bias term, which is why there is no constant bias term in the equation. The rho densities and cells contribute towards capturing the lonely stroke, and the mu densities are responsible for the repeatable region. Through qualitative analysis, we found that extending the input range to a value, which results in the inclusion of one additional column, leads to the best results. The proof of this can be found in our paper. The inverse compensation algorithm presented in this work is adopted from previous studies. Basically, the inverse compensation problem is that given the input history and the desired output, the required input has to be determined. It is an iterative search algorithm, and one requirement of this algorithm is that the input-output correlation has to be monotonic in nature. The algorithm consists of the following steps. In the first step, the output at the current input is computed. The current input can be derived from the input history. Next, the computed output is compared with the desired output, and if they are equal, then the current input is selected as the required input. Otherwise, the current input is increased or decreased by a small step value, and the steps are repeated again. This way, the required input is determined. Coming to the experimental results, first the model identification results are presented in this slide. The level of discretization of the proposed model was selected to be 13, and the IEXT value was selected to be negative 0.95 volts. This value ensured that only one additional column is included in the Prisarc plane. The results obtained by the proposed model are compared with the traditional Prisarc operator and a second order polynomial model. As it can be seen, only the proposed model captures the behavior with high accuracy in comparison to the other two models. The mean modeling error with the proposed model is 0.09%, whereas it was 0.59% and 1.36% for the traditional Prisarc operator and the polynomial model respectively. The identified model was further verified on two other input-output correlations. Similar to the identification results, the proposed model outperformed the traditional Prisarc operator and the polynomial model in both cases. For the first case, the validation error for the proposed model was 0.29%, whereas the validation errors with the traditional Prisarc operator and the polynomial models were 0.71% and 1.53% respectively. Similarly, for the second case, the validation error for the proposed model was 0.2%, whereas the validation errors with the traditional Prisarc operator and the polynomial model were 1.18% and 2.09% respectively. Furthermore, the inverse compensation algorithm was also tested by making the actuator track an arbitrarily generated desired output sequence. The average control error was found to be 0.34%. This error was deemed to be acceptable due to the open loop nature of the control algorithm. In conclusion, in this work we present the first systematic study on the modeling and inverse compensation of the lonely stroke and hysteresis behavior. We primarily focus on the SCP actuators. However, the findings of this study can be easily generalized to other artificial muscles as well. Figures show the input-output correlations of pneumatic actuators, SMA and SMP actuators, and as it can be seen, the lonely stroke can be noticed in all three plots. The proposed model was verified experimentally in terms of modeling and inverse compensation. As a part of future work, we plan to extend this study to model lonely stroke and hysteresis behavior with different shapes. In this study, we mainly looked at the voltage strain relationship of SCP actuators when the load was switched from a higher value to lower value. However, when the load is switched from a lower value to higher value, the shape of the lonely stroke could be different. Secondly, the present study can be extended to cover other commonly used hysteresis models such as the Prandtl-Lishinsky model. That is all from my side. Thank you for your attention and have a good one.